Hi, good morning, good afternoon, good evening. I know we have hundreds of people from all around the world registered for today's webinar. This is Mike Lennon, and on behalf of SecurityWeek, I want to welcome you to the program today. Just a couple quick items on the logistics side before we get started. Common questions. Today's webinar will be recorded. It will be available for replay later on today, usually less than an hour after the conclusion of the live webinar. Additionally, many people ask about these slides. They are already available. You'll notice a resource list within your On24 interface. Simply click on that and you'll get a PDF copy of today's presentation. Additionally, we do these live for the reason of being interactive. We encourage you to submit your questions via the Q&A box located at the bottom of your web browser interface. Q&A will be saved for the end of the presentation, but feel free to submit your questions throughout while they're top of mind. With that said, I want to introduce to you today's speaker, Andrew Ginter. He is VP of Industrial Security at Waterfall Security Solutions. So, Andrew, I'm going to go ahead and pass it to you because I know we have a lot to cover today.
Okay, thank you very much, Mike. And thank you to everyone for joining us. A word about Waterfall. We are the OT security company. I'm going to be talking about OT and industrial network issues and topics today. The topic is unidirectional remote access into OT and industrial networks. Now, I'm guessing a lot of people have heard of unidirectional gateways vaguely. They know the technology is physically able to send information in only one direction. Nothing ever gets back. And that direction is usually oriented out of OT networks into IT networks, enterprise networks, or the internet for that matter. In my experience, though, a lot of people have heard of the unidirectional concept, and they assume that remote access and remote support are ruled out when we have a unidirectional installation. It turns out that there's a whole range of remote access options for unidirectional communications that are possible, and I'm going to review the most popular here. And by the way, do enter your questions if you have questions. If it's something sort of immediate and urgent, my colleague Mike Furstenberg, Mike, are you there?
I am here.
There we go. He's monitoring the questions. Easy questions he'll answer in line. If something has gone wrong and it's clear that people just aren't getting what I'm saying, I've missed something. I missed a whole slide, something like this. We'll answer the questions in situ. But do enter your questions, and I'm going to go through my material, and most of the questions we're going to try and answer on the end. But it's nice when we get to the end if we have a few questions backed up so we can go straight into the Q&A. So do enter the questions into your question panel as they occur to you. Okay, so let's talk about remote access. Before we start into unidirectional remote access, let's review real quick conventional remote access and why anyone would bother with unidirectional remote access. The diagram is here. Generally, we assume that we start somewhere on the outside of the protected network. It could be out on the internet in a hotel room. It could be on the IT network. Generally, we're connecting into the destination network, the operations network, through many layers of firewalls. I mean, in these installations in practice, it might be through 6 or 8 layers of firewalls. Best practice has a virtual private network, a VPN, connecting from the remote host through the layers of firewalls, ending in a jump host. So this is typically a Windows terminal server or remote desktop server nowadays, they're called. What's typically running in the remote host is remote desktop or VNC or Citrix, and that communication is tunneled through an encrypted virtual private network through layers of firewalls, typically ending in the jump host. From the jump host, there's another firewall and the applications in the jump host. The jump host might be trying to access historical data in an industrial historian database. The jump host might be trying to look at the operator's screens using the same human-machine interface, the HMI software that the operators use. And there would be connections open through the firewall into the OT network from the jump host so that someone landing in the jump host can bring up those applications and gain access to the industrial data. So the remote client could be anything, anywhere. It could be an internet kiosk, not generally recommended. We could be sitting, in a hotel room reprogramming PLCs that control $1 billion refinery or a railway switching system. Again, not recommended, but it's possible. And this is part of the problem. If someone malicious gets hold of this system that can do basically anything, there's a great deal that we don't actually want anyone to do remotely, much less a malicious adversary. So let's dig a little deeper. Just how would anybody malicious get into our remote access system? Fundamentally, what we have here is, intervening networks and firewalls set aside. Fundamentally, what we have is two applications on the remote client and on the industrial server, or the jump host for that matter. We have two applications talking. Think remote desktop and a remote desktop server. There's a layer of VPN in between. These applications think they are communicating directly, but in fact the VPN is changing the packets on the way out and unchanging them on the way in. So the first way to attack this is with what's called a man-in-the-middle attack. And this is what the VPN is designed to defeat. The VPN provides a fairly high but not perfect degree of protection against man-in-the-middle attacks. Someone looking at the packets as they come across the internet and somehow stealing the information in the packets or inserting unauthorized packets into that stream. I say the VPN offers a degree of protection provided the encryption keys aren't stolen, or the encryption keys aren't weak, or the algorithm is not weak, or the random number generator is not weak. Random numbers are essential to cryptography. As long as we have a robust system here, we get reasonably good protection from man-in-the-middle attacks. The problem is, this is not the only attack that we face. So, even if the key is intact, even if the crypto is strong, all VPNs are software. And all software has bugs. I wrote software for 25 years. In spite of my best efforts and the best efforts of all of my colleagues on the development team, every piece of software I ever produced had bugs left in it. This is the nature of the beast. People aren't perfect. Some of those bugs are security vulnerabilities. Some of them, we, the good guys, have found and have fixed and have patches available. Some of them we haven't, and our enemies may have found already. 0 days. So what it means is that attackers on the intervening networks don't need to break the crypto. They don't need to just be looking at the packets and trying to do the math and break the crypto. As long as our attackers can make their attacks look like VPN traffic, they could be sending attacks straight into the VPN layer of this encrypted solution and exploiting vulnerabilities, defects in the VPN software. They might be, the most common defects create unauthenticated sessions. So, someone attacking from the internet can connect to the VPN even though they don't have the keys because they've exploited a defect in the software. Some of the vulnerabilities allow remote code execution, so malware can jump from intervening networks through defects in the VPN server, known and 0 day, into the host. A different thing that we worry about with this conventional system is, VPNs are crypto systems. They encrypt stuff, they decrypt stuff. The problem here is that if we, crypto systems are reasonably strong protection against man-in-the-middle, but what we have in this scenario is malware on the remote client. If we've infected the laptop in the hotel room, if we've infected the application, remote desktop or a web browser or something, if we have malware running on one end, that malware can send attacks through the encrypted network into the industrial network or into the jump host. And the VPN, the crypto system, encrypts the attack just as readily as it encrypts legitimate information. VPNs are reasonably strong protection from man-in-the-middle attack. They do nothing for us when it comes to compromised endpoints. So, if we have a jump host, we risk infecting the jump host. If we have a direct connection into the industrial network, which is not recommended, we risk propagating malware directly into the industrial network. So one more here. I just wanted to point out that, even when we have remote desktop into the jump host, best practice is use multi-factor. Use at least two-factor, use a dongle, use your cell phone, use something. The problem is that multi-factor authentication systems are software themselves with vulnerabilities. An increasingly common multi-factor device is our cell phone. And so an increasingly common attack on multi-factor authentication is SIM-jacking. What is SIM-jacking? Do some homework on social media. Learn about our target. In particular, learn their cell phone number and learn some personal information about them. And then go into a store. Do it on a Wednesday evening when, the store is deserted just before closing. Go in and find the most expensive cell phone in the store. Go to the clerk, who's on commission, and weave a tale of woe. Persuade the clerk that you've had your cell phone stolen, and you're on a business trip and you urgently need exactly that model of cell phone back. Would they sell you this very expensive cell phone? Yes, of course. Yes, sir. Yes, ma'am. Can I sell it to you now? And persuade them that you need the victim's, in quotes, phone number connected to this cell phone. Give up the information you've stolen about your victim so that you persuade the clerk that you really are the victim. And, they want to be persuaded at this point. Have them connect the cell phone to your victim's phone number, and now you're receiving the victim's phone calls, you're receiving the victim's text. You log into the system, it texts a one-time code to your cell phone. You get it on your SIM-jacked cell phone, and you're in. So, log in, and if I may, you do have to steal the password. Again, there's some phishing required here. You need not just the cell phone, which is the hacked multi-factor, but you have to have stolen the password as well. You need the password and the cell phone to get in. So this is why we're worried. And, this is not just a theoretical, discussion here. There's countless. These are some of the most serious vulnerabilities that have been reported in the last, 1, 2, 3 years, 2.5 years, against VPNs, against firewalls, against remote desktop and other remote access clients. So, thousands of these vulnerabilities are reported every year. A fraction of them are unauthenticated access vulnerabilities, remote code execution, or the ability to steal the VPN keys and the cryptographic keys that protect us from the man-in-the-middle attacks. Now, if I may, these risks may be entirely acceptable on IT networks, on enterprise networks, because what's the consequences of compromise on a business network? Bad stuff gets into our network. What do? We activate the incident response team, the incident response process. We identify the impaired equipment. We isolate the equipment. We erase it. We restore it from backup. We repeat. This is the essential problem on industrial networks. We cannot restore casualties at the site or damaged physical equipment or lost production. We cannot restore any of these things from backups. And this is why the industrial sites that we work with at Waterfall generally do use all of this software-based remote access on their enterprise networks, but they generally use something much stronger for their OT and their industrial networks. So, what do they use? Let's go through a concrete example here. Here's one use case, and really what they use depends on the use case. So here's one use case. We have two applications communicating. One application is remote on the right side here. This is at the vendor. This is, the vendor is across the internet. We call it cloud. That's the new term for vendors across the internet. We've had vendors across the internet in the industrial space for 30 years, but nowadays everyone calls these cloud vendors. Fine. On the left we have the industrial system, an industrial application, the vendor's industrial application. The vendor wants to monitor the industrial application 24/7 in order to identify problems before the customer notices them and fix the problems before the customer notices them, or to do big data analysis and suggest optimizations that the customer may not have considered yet. So, how does this work? Typically, we set up a virtual private network, a VPN connection, through many layers of firewalls, straight through all those layers, between the vendor's site, where they have all of these big data analysis, gather the data and crunch it capabilities, and, many client sites, many customer sites. The applications at the vendor site query and I've got the wrong word here. That's supposed to be query on the top there. The vendor's applications query the industrial application, and we get responses back. The next slide here, I was going to say, the problem is this. What happens if the vendor's site, the vendor's systems, have been compromised? The VPN to the industrial site will encrypt attacks from a compromised vendor just as readily as that VPN will encrypt legitimate communication. So now the attack code that has taken over some or all of the vendor's application is sending attack messages into the industrial site through the VPN, through layers of firewall, and getting responses back from its victim software. What does this mean in practice? Well, these cloud vendors are typically connected, each of them, to tens or hundreds of networks. The average large industrial site is connected to at least a half dozen of these cloud vendors. In some industries, it's dozens of these connections. The manufacturing industry has got dozens. The process industries, power plants tend to have a half dozen. Refineries tend to be somewhere in between. And the trend is accelerating. Every industrial vendor out there is either selling or building remote management capabilities. Why? Because continuous access to the vendors, the customer having continuous access to experts at the vendor and expert systems that the vendor has put together. This is a powerful value proposition. The vendor fixes problems before we even notice them. Within a handful of years, I predict that the average industrial site is going to have dozens of cloud connections, and the maximum is going to be over 100. So let's look at this. Lots of industrial sites, each connected to lots of vendors. Each of the vendors is connected back into lots of other industrial sites. Some of these industrial sites are going to be thoroughly protected, thoroughly secured. Some of them are not. This is the nature of the beast. Not everyone's the same. It is inevitable that attackers are going to get into some of these poorly defended industrial sites. Then what? Well, then, having compromised a site on the lower left of the diagram there, those attackers have an opportunity to attack any of the cloud vendors, any of the cloud services that are connected to the site through VPNs. Now, some of those cloud vendors are going to be thoroughly protected and immune to the attack. Others are going to be less secure and are going to be compromised. Not all of the vendors are the same either. The more vendors you have connected, the more likely it is that at least one of them has very weak security. It is inevitable that one or more of these cloud vendors is going to wind up compromised. Now, we've got a compromised vendor. That gives the attackers the opportunity to pivot their attacks through the cloud, through the compromised vendor, into other industrial sites, using the VPN connections, the remote connections, deep into those other sites through layers of firewalls. Some of these connected sites, you might have a small vendor, poorly defended vendor, but that vendor is likely to be connected to a lot of customer sites. Some of those customer sites that the vendor's connected to are going to be large and well secured and prime targets for attack. The vendor connection is a back door into these large, valuable industrial targets. The vendor VPN reaches straight into them through all of their heavily defended, through all of the heavy defenses that the site has in place. So, having talked about the problem, let's talk about the solution. I said, we're going to talk about unidirectional remote access. The first thing we have to understand to wrap our heads around these remote access technologies is exactly what is a unidirectional gateway. Now, we all know that, vaguely it's one way. In this diagram, everything inside the red in the center is the unidirectional gateway. It's a combination of hardware and software. It's usually packaged as a 1U rack mount device, but I've called it out as 3 separate devices here to highlight the fact that there's a conventional computer, a CPU, that's part of the 1U rack mount solution on the left. There's a CPU on the right, and there's the special hardware in the middle. The special hardware is able to send information in only one direction. There's a circuit board on the left here inside the box that has a fiber optic laser in it, a transmitter only. It has no receiver. There's a short piece of fiber. This piece of fiber is generally, 18 inches long. Connects to a circuit board on the other side. The circuit board on the other side has a photocell, a receiver, but no laser. So there's no laser. There's no sender on the receiving circuit board. There's physically no way for that circuit board to send a signal back down the cable to the sender. The sender has no idea if the receiver, even has power. There's no signal at all coming back on this fiber optic. So the gateways are a combination, and this is not my terminology. This is NIST terminology. If you look at NIST 882, that's the standard for NIST standard for industrial control system security. Look at their definition of a unidirectional gateway. They define the technology as a technology that sends information only one way in the hardware. That's the hardware that sends one way, and software that makes copies of servers. So what does that mean? How can we do remote access to? Well, what are we making copies of? What happens is the software on the inside CPU, the sending CPU, connects to a database. It might be SQL, it might be a Pi historian, it might be something else. It might be an OPC server. Connects to some sort of data source. Logs in normally, username and password, no reverse engineering, nothing tricky here. Just logs in as a normal client and asks the data source for all of its data. Converts the data to the weird one-way formats, and on the other side, the software logs into an identical server. If it's SQL on the inside, it's SQL on the outside. Pi on the inside, Pi on the outside. Wonderware Orchestra historian on the inside, it's Wonderware Orchestra on the outside. Log in with a username and password and insert all of the data into the replica. Now, anybody on the enterprise network, anybody at a remote vendor across a VPN through the internet, anybody on the outside who wants that data asks the replica for the data and gets the same answer as the live system would have given without ever sending even a query, nothing, back through the hardware. So that's the secret here. It's a combination of hardware and software. The hardware is physically only one way, and the software replicates stuff. So in this example, we were talking about a compromised cloud vendor. If we are replicating the turbine management database so that a turbine vendor, GE, Siemens, ABB, whoever, can look at the data and predict when the turbine is going to fail and schedule maintenance of the turbine optimally, well, they've got a VPN now into the replica on the enterprise network. They're getting all the live data. They're able to draw all the conclusions they need to draw. They can't tell they're working with a replica. The cloud vendors are happy here. And if we have a unidirectional gateway deployed, as we do on the right-hand 2 sites here, even if a cloud vendor is compromised, the worst they can do is compromise the IT network, which is a big deal, but it's not affecting physical operations. The worst they can do is compromise the turbine management database and confuse it. But they're compromising the replica. It's not physically possible to send anything back into the industrial network. Chaos can consume the enterprise network while we rid ourselves of this wretched compromise. But on the industrial side, the lights stay on. Gasoline keeps coming out of the refinery. Physical operations is oblivious to whatever might be happening on the enterprise network. And this is by design, so that if we're unidirectionally protected, nothing gets in. What we've done here The vendors require remote access. They require remote access to the industrial data. They don't need remote access to the industrial systems. Unidirectional gateways give you access to data without giving you access to systems. But, I hear people in the audience getting restless. I promised you remote access. I talked about remote desktop. Remote desktop shows you screens, not cloud data. It's great that unidirectional gateways can meet the need of that one use case where you got cloud vendors. This is an emerging threat. Great, we got that. What about screens? I want to see the screen. Let's talk about remote screen view. In this scenario, and again, every different scenario deserves a strong, specific solution. In this scenario, we have a remote vendor. Let's say it's that same turbine vendor. The turbine vendor has discovered that there's a hotspot in a gas turbine and needs to adjust the control system to compensate for the hotspot so that it doesn't turn into a failure where we have to physically take the turbine apart and repair it. We want to compensate for the bit of a defect, a bend that has evolved in one of the turbine blades. How does this work? The vendor sees the problem, sees a problem building up, and says, "Okay, we got to fix this," and calls the site and says, "This is your vendor. You've got a problem in generating unit number 3. Can I have an hour at 3 o'clock on Thursday to fix this problem?" The site says, "Yes, of course." They schedule an hour. 3 o'clock Thursday, an engineer is sitting down in the power plant. The engineer is sitting in front of the turbine management workstation and physically picks up the cell phone and calls the vendor. The engineer knows who they're calling. Okay, this is not a random phishing phone call coming in. They know who they're calling. They get the vendor, they get the support technician, and they say, "Okay, are you ready for this?" The support person at the vendor side says, "Yep, fire up." And so the engineer at the site turns on remote screen view. What is remote screen view? It is like remote desktop. It starts taking pictures of whatever's on his monitor or her monitor, as the case may be, sends those pictures out through the one-way hardware, and stands them up on a web server on the outside. Now, the vendor uses their VPN connection into the customer network to access the enterprise network web server that holds the pictures of the screen, holds basically a video feed. A standard browser connects and they see what seems to the browser to be a video, and they see the screen there. Now, the vendor can move their mouse all they like. They can bang on their keyboard. Nothing gets back through the gateway. It's not physically possible to send any signal back, but there is a connection on the cell phone, and the vendor says, "Okay, bring up the vibration diagnostics," and can see the mouse moving and can give real-time advice. No, that's system diagnostics, 2 further down. There you go, that's vibration diagnostics. And together, they fix the problem. Now, the vendor sees this process as supervising personnel at the site in the course of a complex correction, because they want to make sure their policies and procedures have been followed correctly. The site sees the problem differently. Whose turbine is it? It's not the vendor's turbine, thank you. It's our turbine. And I want to know what the vendor has done to our turbine. And so the engineer at the site is not a mouse monkey. The engineer at the site is asking questions. The engineer at the site moves the mouse only when they understand why they're moving the mouse, and they've decided that that's the right thing to do right now for this turbine, and it's not going to impair operations at the power plant. So the site sees this as supervising the vendor. The site engineer is taking notes. They want to know what the vendor has done to our turbine. Thank you. Remote screen view meets both sets of needs. The vendor's needs are met. The engineer at the site's needs are met. So, and if I may, in this world of quarantines and travel restrictions, a couple of weeks ago, Waterfall decided we have to help our customers. A lot of our customers rely on service providers physically to come out to the site and do stuff. Our customers are, of course, unidirectionally protected. That's what we do. And so as of a couple of weeks ago, Waterfall is giving away free remote screen licenses, as many as customers need, to any existing customers. I say existing customers because you have to have the hardware in place if you want the remote screen view license to work. If you have the hardware in place, using the license is a matter of putting it in and activating it, and now you have remote screen view. And these licenses are good through at least the end of September Q3. So something we're trying to help with a lot of sites who suddenly discovered they need this kind of remote access where they didn't before. But you might ask, back to remote access, remote screen view is our most popular unidirectional remote access mechanism, but it's used primarily for untrusted third parties. Now, what's that mean? What's trust mean here? If we call support, let's say I've got a weird error message that appears to be coming out of the Microsoft operating system, because Windows is used throughout these industrial networks. I've got a weird pop-up, and I know I'm in trouble. I call support. I get a voice on the phone I've never heard before, in some distant city or on another continent. The first thing they say is, yes, connect to your remote access web server, connect to our remote access web server, connect your site, download some software, connect to the site. I will take over your screen. I will figure out what's broken. I will fix it for you. These people are outsiders. They've had no background check from the site. We haven't given them a background check. They've not been through our safety training. They don't know what's safe to do on our networks and what's not. They're not part of the security training. They're not part of the security awareness program. They're not part of the safety awareness program. These people are outsiders. Remote screen view works for them. They can look but not touch. An engineer on the inside decides if what they're going to do is safe. That engineer has been through the safety training, the security. They've designed the safety training and the security training. So remote screen view works for that untrusted, but what about a trusted insider? What about people we do trust, people who have, who can breeze through our security because they're that trusted? They can walk to any part of the plant. They can do things without supervision. They've been through all of our training, all of our background checks. What if they need remote access? It doesn't make sense that they have to go through a third party inside the plant. Well, for these trusted people, we have something called secure bypass. This is a class of technology that unidirectional vendors use for remote access for trusted insiders. Here's a scenario. Let's say an operator sees that their HMI is slowing down. It's not yet stopped, but they can see that there's a problem building up here. They pick up the phone, they call the engineer on call at 3 in the morning. The engineer on call hears the problem description and says, we need to fix this. He calls 3 of his own people. They, pile into their cars and drive to the site, but it's going to take him half an hour to get there. So during that half hour, the lead engineer asks the operator on site, before you go back to, dealing with your system, can you walk over to the key closet, pull the secure bypass key out, stick it into the device, and turn it? And then the operator goes back and does their work again. What does this do? The secure bypass device is copper in, copper out. And most of the time, that copper is physically disconnected inside the device. There's electromagnets inside the device. When the copper is physically disconnected, nothing gets through in either direction. When you turn the key, it activates, the electromagnets. They temporarily enable a two-way copper connection. So now we have gigabit in and out, and we don't activate this connection in parallel. Between the internet and the industrial network. You generally activate it between an enterprise network, so the engineer VPNs into the enterprise network, between the enterprise network and a jump host. Well, comes through the device, goes into the jump host, and now starts trying to diagnose a problem, trying to fix a problem. Half an hour later, his people call him, say, we're on site, get in here. He says, thanks, logs out, gets into his car, and, drives to the site. Hours later, they've fixed the problem. Everything is settled down. Nobody's remembered to take the key out of the device. The device is still sitting there, but that's okay because it has a hardware timer in it. It might be 30, 60, 90 minutes, whatever the site has decided. After that period of time, the key automatically pops back. The electromagnets automatically disengage. Now, you are physically disconnected from the world again until the next emergency. So if you need a trusted insider to come in, here's a technology that's typically deployed in parallel with your unidirectional gateway. The gateway is one way out continuously, and this device, the secure bypass, is activated as needed in emergencies, or if you need help from IT to install a bunch of security updates or something. Anytime you need remote help from an insider, from someone who's been through our checks, who we trust, this device gives us physical control over when people can connect remotely. Almost all the time, it's disconnected. Nothing gets in. And in brief periods of emergency, or when we need remote help, we activate it, and we have all of the usual software-based protections in place for the duration of a short session. There we go. So let's move forward. So that's physical control over access by insiders, occasional access by insiders. What if we have a different need? What if we need continuous 24/7 remote control of a unidirectionally protected site? For example, we might have a large power plant. We might have two smaller nearby natural gas plants. The large power plant has a 24/7 operator. The two smaller plants, they've only got a 5/8 operator. Off hours, control of those two plants is turned over to the central operator. Or we might have, an IT team at head office. We might have a central engineering team. We might not have any engineers in our plants anymore. They might all be sitting at head office on another continent. And what do they do all day? Well, they log into one or another of these systems all day, 8 hours a day, and do their work. So secure bypass doesn't make any sense for that scenario because it's turned on all of the time. So here's a different solution. What we see people who have unidirectionally protected networks do, and they have a need for continuous remote operation, what they do is they design their networks in a particular way. So they will lease communications capacity between these sites. You see the sites on the bottom, 3 sites, a central site and 2 subordinate sites. It might be head office and 2 refineries. It might be a large power plant and 2 smaller power plants, depends on the scenario. But on the bottom here, there's leased capacity. This is T1 or MPLS or whatever the current way to lease packet switch capacity between these sites is. This is not a public network. Okay, you can't get to these wires from the internet. And what we've done is we've connected up all these sites that have access to the industrial systems, and we're modeling them as one control-critical wide area network. In principle, any device anywhere on this network can reach and touch anywhere else in the network. There might be some firewalls in place, there might be some encryption in place, but it's all software. The hardware, there's no hardware protection between these sites, and so these sites are modeled at the same level of criticality. So what's that mean? It means that if any of these can, in principle, get anywhere else, they all need to be protected to the same degree, the same way. They're one network. So if we have unidirectional protection, we typically see a gateway, a unidirectional gateway at each site. Now, practically speaking, the large sites, the central sites, it makes sense to put most of our unidirectional connectivity there because there it's easy to manage. We always have people there. But across these leased connections, we typically pay for capacity. Capacity is cheap nowadays, but it's not that cheap. If we're doing something nasty like, replicating a mirror port, unidirectionally replicating a mirror port of, hundreds of megabits per second of industrial network traffic on the left there out to an intrusion detection sensor on the plant's enterprise network, it makes sense to do that locally, not to send all of those hundreds of megabits per second across to the head office where it pumps out unidirectionally. So typically what we see is a gateway in each of these sites. The central gateways tend to be more complex. They have many more replications configured. The gateways in the remote sites tend to be specialized to whatever local high volume connectivity they need. What this means as well, so practically speaking, what does it mean at the central site? At the central site, it means all of the computers that have access to this network are part of the industrial network. Whatever physical security we have in place at these satellite industrial locations, that same physical security must be in place at the central site. If there's guards, gates, and guns around our power plants, we need guards, gates, and guns around our central office, or at least equivalent protections. We need a secure area inside the office building, typically a floor or an area within a floor. You've got to badge into that area. Only authorized people are allowed in there, because if you touch the wrong machine in there, you're reaching and touching. You have consequences, physical consequences at one of these sites. You tend to have a mix of machines in there. Every engineer's office or every IT person's office tend to have 2 machines in there. There's, one machine painted bright red saying danger. This is on the industrial network. Things you do here have consequences. The other one is whatever color you want, and it's on the enterprise network, and you use it to do dangerous things like browse the internet or read email, and never the 2 networks shall meet. So, this is a design pattern that we see for unidirectional networks that require continuous remote operations. Missed anything here? Not really. So what the design gives us is continuous, whenever people at the site want, gives us continuous on-demand remote control, gives us remote control from specified, physically secured, cyber-secured sites that are part of this private, control-critical wide area network. So that was 4 unidirectional remote access designs that, each of them is stronger than a firewalled VPN software-only system. Here's a reminder of why these designs are important. The cyber threat environment continues to worsen. President Trump just declared that cyber attacks on the power grid constitute a national emergency. In this era of quarantines, ransomware authors are targeting remote access software specifically. There's new ransomware out there that's targeting industrial sites specifically. It's designed to understand dozens of the most popular SCADA systems and more. I talked about the 4 most popular remote access designs. In practice, we see a lot of variations on those designs. This is why I wrote a book on this topic. This is my latest book. It documents what I see the world's most secure industrial sites doing. And, by the way, Waterfall has an inventory of these books. If you're interested, we're giving them away for free. You can request a copy at the URL at the bottom of the screen there, waterfall-security/SecOT. What does this mean? Well, to a man with a hammer, all the world's a nail. To a man with a firewall, all the world is another open TCP port. Encryption is the answer. What was the question? What we've seen is how to defeat encryption, how to defeat firewalls. Here's an alternative. In Chapter 6 of the Black Book, I document 20 network designs. And the philosophy here is disciplined control. We want to be very careful of the ability to remote control our sites. What I've shown you is 4 different remote access designs, each of which meets a different business need. At Waterfall, we designed the most specific, the most secure solution to specific business needs. It's not a one-size-fits-all. It's not bang, another open TCP port, next question. And, again, Waterfall's leading the way. We're giving away the books. But if I may, getting the books does no good if you don't read it. It is an easy read. Probably takes 7 to 8 hours. It's not that, that down in the weeds. Get through it and let me know what you think. A few more words about Waterfall. We are the OT security company. We've been around since 2007. We've got thousands of sites. We're headquartered in Israel. We are a product company. We sell product. We sell technology. We don't sell services. If you want a consultation, if you want even an on-site consultation where one of our solution architects comes in and looks at your network and makes some recommendations, there's no charge. Help us understand your needs, and we will propose typically a couple or 3 strong unidirectional options to meet those needs. and explain the different trade-offs between the different architectures. One more resource if you're interested, the Industrial Security Podcast. It's available on all your major platforms, you know, your favorite iPhone podcast app, your favorite Android podcast app. Waterfall sponsors it, but it's not about Waterfall. This is a public service. It's about industrial security. Every episode has a different expert guest. You know, we're on to episode like 36 or something. We have guests from all over the spectrum. We have technical people. We have you know, people who are on boards of directors talking about cybersecurity governance. We have government agencies. We have recruiters. You know, we have educators. So if you're interested in the topic of industrial security, you know, check out the Industrial Security Podcast on your favorite platform, or come to the website waterfall-security.com/podcasts. So that's it. Let's wrap up. The threat environment continues to get worse. The potential for physical consequences of compromise at OT sites, you know, the potential is unacceptable. If you look at how strong industrial sites are, how many are how strong, you know, give us, I don't know, 10 measures of strength, count how many sites are at each measure, you're going to get a curve. It's, you know, it's a large random population. It's going to look something like a bell curve. Because the threat environment continues to get worse, all of us continue to increase the strength of our security posture. The entire bell curve of security posture strength is moving to the right. It's moving in the direction of sites that currently practice secure operations, that currently do what I document them doing in Black Book. I didn't make this stuff up. I'm documenting what the world's most secure sites do. I suggest then that these techniques lie in all of our futures, and I recommend that people become familiar with them and start picking and choosing which of these techniques make sense to use today, and which are we going to leave for tomorrow, and which are we going to leave for the day after that, because these are coming. You know, the world is becoming a more threatening place security-wise. We need to get stronger about protecting our industrial networks. I've reviewed the four most popular ways to provide remote access into unidirectionally protected industrial sites. Server replication lets us access data remotely without accessing the systems remotely. Remote screen view is used routinely for outsiders, people we should not trust to wander around our control systems locally or remotely unsupervised. Secure bypass provides us with physical control over who connects remotely to our sites and for how long. And continuous remote operations is a design where entire control-critical wide area networks are all unidirectionally protected, physically protected to the same degree as their most sensitive site in those networks. And those sites can reach out to each other. Physically secured sites can remotely do whatever they want remotely because they are protected as strongly as the industrial sites. They're part of the industrial site. The philosophy of secure OT sites, all attacks are information. Every bit of information can be an attack. We have to control the flow of attack information. We have to control those flows physically, not just with software. When you read the book, I'd be grateful for any feedback you might have. My email is right there, andrew.ginter@waterfall-security.com. I'm grateful for all feedback, good, bad, or ugly. I can only improve future work, and I am working on a new book on OT risk management options. I can only improve if I get feedback, so don't hesitate to reach out to me. So to sum up, don't just open another VPN TCP port for remote access. I encourage you all to deploy something stronger. Deploy the strongest protection that is specific to your business needs. That's what I had. Thank you for listening. Mike, do we have any questions?
Okay. Yeah, thanks, Andrew. Very, very interesting stuff. We had a ton of interaction from the audience as I watched through there, so it's certainly looks like it's interesting to the audience, which we always like to see. So we get about 10 minutes, and I'll get through as many as we can. Okay, this is one which might be appropriate for a number of people in regional utilities, etc. The question is, what do you recommend for smaller operators who have very limited budgets, especially now? They may have at best hundreds of dollars, if not thousands, on these best practices. Where do you start, and how do you get the most bang for your buck
That is a tough one. I do have a white paper in the works now. It's stalled. Sorry, I got distracted with all this COVID stuff. But I did have a white paper in the works. I was working with not power utilities, but small water utilities. And what we're going to do is answer that question specifically. If we've got a small water utility, what does it look like? What are the risks? How is it usually automated? We don't have, some of these small utilities, they hardly have a full-time IT guy for the whole town, much less a SCADA security guy for the water systems industrial network. And so the short answer is we're working on that. The long answer is I would encourage you to grab a free copy, free of charge, of the Black Book, and have a look, not just through Chapter 6, which is talking about unidirectional, this, that, and the other thing. Look at Chapters 3 and 4. 3 talks about the philosophy. All cyber attacks are information. That's what cyber means. All cyber attacks are information. If we can control the flow of information, we can control the flow of attacks. So, do you need the utilities water system to be connected to the internet? Not need as such, no. What can we do about controlling the number of connections, controlling the highest risk elements of the problem, controlling people carrying USBs in? What can be done? There's some ideas in Chapters 3 and 4, but to be honest, a lot of the customers I work with are the larger ones, and so I am working with engineers who serve small customers to try and put together your answer. So that's a very long way of saying I don't know, but I'm working on it. And stay tuned, because we'll be publishing the white paper hopefully later in the year.
Absolutely. I'll keep an eye out for that myself. Okay, another one, and this is the patching issue is something that always comes up at our conferences especially. But this question is specific to this architecture. So the question is, in this architecture, what in your opinion, is the best way to update the OT devices of the OT layer? Assuming that you have...
Well, that's complicated as well. Security updates are the most costly element of most industrial sites' security programs. They cost an enormous amount of effort and labor, and they introduce almost as much risk as they mitigate. What's the point of a security update? It is to hopefully fix known vulnerabilities. Why is it a problem? It's because every change to the industrial network is a threat to correct operation, a threat to safe operation, a threat to reliable operation. And this is why when we do security updates, we have to test them exhaustively. First the vendor tests them, then the control system vendor tests them, then we have to test them, because our configuration is typically unique. There's these systems that we're running are not cookie cuttered. They use the industrial market is highly fragmented. There's pieces from all over in a typical industrial control system, and the configurations tend to be unique. And so, do we know, how confident are we that a certain security update that's been tested by the vendor of the update, that's been tested by, let's say, the operating system vendor, Microsoft or Red Hat, and it has been tested by the control system vendor and blessed by the control system vendor? How do we know it's going to work for us? Because our environment is unique. We have to test it. The testing is costly. It's just a very expensive process. We can't just press a button and automatic update. If there's a blue screen in a refinery, we're down not for an hour, we're down for days, if not a week and a half, trying to come back up to full production. You can't just turn a switch and turn these things on again. So how do we do it? We do it very, very carefully over a long period of testing. We deploy it, first on the least important equipment on the site. We get some experience with it. Is it blue screening? Is it working for us? We deploy it on redundant equipment. We fail over to the new software, see if it works. If there's a problem, we fail back it out. So the short answer is it's long, it's expensive. Often, IT personnel do provide assistance to the site personnel to do these updates. And they will do it through one of these remote mechanisms. Typically, if they've been through the training, either secure bypass or by badging into a central area where we're controlling all of our stuff remotely, and they're looking over the shoulder of the engineers, and they're doing very carefully, very cautiously these security updates. That was a long answer, but I hope that answers it.
Yeah, that's kind of what I expected, but it is so common. I at least touch on it. Okay, this is an interesting one, a little bit theoretical, but we'll go there. So this question or comment combination is: could an OT site launch an attack on a vendor's cloud network, then once compromised, escalate the attack to further additional OT sites? In other words, so an attack from an OT site to an OT site via vendor's cloud infrastructure.
So I'm guessing that question came in early in the webinar, because that's exactly the attack scenario I tried to go through. If that didn't come through, shame on me. That was the scenario I was trying to explain, the first concrete attack scenario, where you take over one of the plants on the diagram, goes red, it attacks the cloud site. The cloud goes red. Now the cloud can attack all the other sites, even if they're heavily defended, because it has a VPN deep into the site. Yeah, this is absolutely. And if I may, this is not just me talking. FERC, the Federal Energy Regulatory Commission in the United States, recently issued a request for comments on what should they do about 6 different things. One of them including all of these cloud connections. Should we be worried? So I responded. I gave exactly this attack scenario. So yes, the short answer is yes, be very worried. The long answer is but. If you have unidirectional protection, a unidirectional gateway between the stuff that is connecting to the cloud and the cloud, then nothing can get back in. The cloud systems still work because they have access to the data. They don't have access to the systems. They cannot compromise the systems. That's what I was trying to get through on slides about, 4 through 8 or something like that.
Yeah, maybe they joined a little bit late. It was interesting. Okay, and this I don't know how particularly you want to get on vendors, but this question is interesting. Your attendee is saying that I'm joining from Nigeria. My company is currently about to commission a modular refinery. The vendor will be connecting from the U.S. to monitor and work on the MCC of the modular refinery. What firewall would you recommend?
Well, I don't recommend a firewall. For that need, I recommend the continuous remote operations design pattern on slide, let me look here and find it, slide number 21. And so I would not recommend that the vendor from the United States log in over the internet through firewalls with VPNs. That's software. What I would recommend is lease communications capacity. Doing that to Nigeria is a bit of a challenge. You might have to lease satellite communications. You have to lease something, but do not put just software between the internet and your plant in order to enable remote operations. Allow remote operations only from sites in the United States that are as physically secure as the refinery that's being protected. And this is described in Chapter 6 as well. It's one of the design patterns, one of the 20 design patterns in Chapter 6.
Okay, another one, and this goes back to your VPN attacks that you mentioned earlier on in the presentation. The question is, would blocking split tunneling protect us from those VPN attacks?
Yeah, so I have not gone through the complete list of possible protections, software protections, but my point is that software is software. But let's speak to split tunneling. That's the question. Split tunneling is where we have a VPN on a computer, and we are tunneled through the VPN into the industrial site, and have an opportunity then to attack the industrial site. And we are permitting at the same time connections to the open internet. Why is this a bad idea? It's because if there's malware on the computer that's, let's say, taken control of the remote desktop screen, made the screen disappear, put up a useful error message like remote desktop is not responding, click here to get help. And when you click here, nothing happens, and the person picks up the phone and reams out support. And for that whole half hour, the remote attacker is using the invisible window, clicking on it, doing things remotely across the internet because we're connected to the internet as well as to the VPN. A lot of, remote access best practice documentation will say when you're connected through the VPN, disable connections to the internet. So the only place you can connect is to the VPN. You can't get out to the internet anymore. If there's malware that tries to take control of your remote desktop screen, it can't do anything because there's nobody who can control it. The problem with split tunneling protection is that it's software. If you have sort of commodity malware, common malware, stuff that's designed for your remote control of enterprise networks, yeah, it might not recognize the split tunneling thing, and it might be defeated by that split tunneling protection. But anything that's protecting split tunneling is software. If you've got a piece of malware that's designed for taking advantage of taking over remote access sessions, it can re-enable split tunneling. It can do its own, internet protocol stack, interact with the hardware itself. Once you've taken over a CPU with your own software, that CPU can do any dangerous thing the CPU's able to do. If it's physically able to send messages out to the internet, and yes, it can, because that's what it's doing with the VPN, your malware can make it do that on its behalf as well. So there's another half dozen mechanisms, software mechanisms people use. All software can be defeated, is my point. So I hope that makes sense.
It does. So we are out of time, but there's a few more questions. I'm going to try and squeeze in one more, if you don't mind, Andrew. I apologize for everybody. We had a ton of questions. We weren't able to get to them all, but we'll try and reach out to you individually if there's something, and you can also contact the folks at Waterfall or SecurityWeek. But there's one more I want to try and squeeze in before we wrap up, and that's, can you do true remote desktop with two unidirectional gateways using one into the network and one out?
Yeah, that's a tricky one. The short answer is no, don't do that. The long answer is, there's like 50, 60, 70, I've lost track, unidirectional vendors out there. And bluntly, some of them sell snake oil. So, why is that snake oil? Well, imagine a twisted pair Ethernet cable, just a common cable. I have them all over my desk here. Even in this world of wireless, I still have cables. Take it apart. What's inside? Conductors. One pair of conductors, the voltage difference between them is a signal that is sending from my computer out to the world. Nothing comes back on those conductors. The other pair of conductors has signal coming back. We have one way out on one pair of conductors and one way back in on the other pair of conductors. How much security does that wire give me? None. If I have two unidirectional things and they're forwarding packets between one network and another in one direction, and the other one is forwarding packets back the other way, that's what a wire does. So it is possible to do unidirectional gateway in, unidirectional gateway out, and achieve a security goal. Typically, basically, as long as you're never forwarding the contents of packets. If you take the contents of packets from one network, run them through the hardware, and stick them into packets in the other network and send them on their way, you've done nothing. And there's vendors out there who do that and claim that they're deriving a security benefit. If instead you're replicating one set of servers in, let's say you're replicating antivirus servers and WSUS servers in, access that security information on the inside network, replicating historians and syslog out, SEM knows what's going on, and your operations data is available to the enterprise. That offers a degree of security. It's not a round trip that remote attackers can use like through a firewall, like a wire. So don't be deceived by people who are saying, I've got one way in, one way out, I can do remote desktop, I can do any protocol you want. anytime, that's an alarm bell. If it says, I can do any protocol you want, it's either doing what a firewall does or doing what a wire does, which is less than what a firewall does. So, buyer beware.
All right. Well, we are now officially out of time. On behalf of Security Week, I want to thank everybody and hope you found this informational. We always enjoy working with you guys as well at Waterfall. And everybody stay safe and be well. And we hope we can all connect in some of the industry events soon when life gets back to normal. But thank you so much. And Andrew, I'll leave it to you for closing remarks.
I just wanted to thank everyone. The PowerPoint's available. And again, don't hesitate to reach out to me or reach out to anybody at Waterfall. We love to talk to people. Like I said, I'm writing another book. I would rather write about problems that are important to you. I'd rather document the solutions that I hear people using that make the most sense, rather than make stuff up and get it wrong. So by all means, reach back to us and let us know what you think. Good, bad, or ugly, it all helps. And that's all I had. So thank you so much, and hopefully we'll catch you on future webinars.